A big moment that showed general relativity was right happened during a solar eclipse in 1919. Sir Arthur Eddington led a team to watch how light from faraway stars bent as it passed close to the sun. According to the theory, the sun's big mass would make the starlight curve a bit. During the eclipse, the observations precisely matched Einstein's predictions, establishing the validity of the theory. Just like motion can change how we experience time according to special relativity, gravity also has an impact on time. In places where gravity is really strong, time moves more slowly compared to areas with weaker gravity. So, if you were standing close to a huge object like a black hole, your clock would tick more slowly than one placed far away from this powerful mass. General relativity introduces the idea of black holes, which are spots where gravity is super intense. Inside a black hole, the gravitational force is so powerful that nothing, not even light, can escape from it. The edge around a black hole is called the event horizon, and it's like a point of no return. Once something crosses this boundary, it gets pulled into the black hole without any chance of coming back. Einstein's theory of general relativity has big implications for how the universe is structured. At first, he added something called a cosmological constant to his equations because he thought the universe was not changing. But when we found out it's expanding, he called this a big mistake. This idea of an expanding universe based on general relativity is a key part of the Big Bang theory, which explains how the universe began. Another important idea from general relativity is about gravitational waves. These are like ripples in the fabric of space and time caused by really heavy things moving fast, like when black holes or neutron stars come together. In 2015, scientists at the Laser Interferometer Gravitational Wave Observatory, LIGO, directly detected gravitational waves, proving another part of Einstein's theory. Over time, scientists have conducted numerous tests to check if general relativity is true, and each time it has proven to be right. Whether observing how planets move, the bending of starlight, or the detection of gravitational waves, the theory has consistently been supported by evidence. While saying gravity is a lie might be surprising, especially since we all experience gravity every day, in the world of physics, it's normal to discuss and explore different ideas. Scientists like Brian often question established theories, and with gravity, some people challenge the usual way we think about this basic force. One idea challenging traditional gravity is called modified Newtonian dynamics, MOND. MOND suggests that gravity acts differently at slow speeds, especially in galaxies, without needing dark matter. Instead of adding invisible matter, MOND proposes that gravity gets stronger at low speeds. The gravity debate also involves mysterious dark matter and dark energy, introduced to explain certain phenomena in space. Critics argue that these are not needed, and alternative ideas can explain the observations. The search for a deeper understanding of gravity is ongoing, and some scientists believe we might eventually find a new framework to replace the traditional concepts of gravity. Time is a complex, layered puzzle, and in the world of physics, our best understanding can change with new ideas and evidence. With Brian Cox's latest theory on time, we may be on the brink of a discovery that changes everything we thought we knew about how the universe works. As we move forward in our understanding of time and gravity, we face new frontiers. The latest advancements, like quantum mechanics and the search for a unified theory of everything, push us even closer to unraveling the deepest mysteries of the universe. Quantum mechanics, for example, deals with the smallest particles in existence, and it presents a world where probabilities, not certainties, rule the roost. This world behaves very differently from the macroscopic universe we see around us, where Newton's laws or even Einstein's general relativity provide a predictable understanding of how things move. Quantum mechanics and relativity have been thought of as two separate realms, with one governing the tiny world of particles and the other explaining the grand cosmos. But scientists are on a quest to merge them into a unified theory, a theory that explains both the very large and the very small in one comprehensive framework. This theory could, for instance, reconcile the nature of time as we understand it on a cosmic scale with the strange, unpredictable behavior of particles at the quantum level. The famous physicist Stephen Hawking spent much of his career exploring these questions, attempting to merge these two schools of thought. His work, along with that of others, has opened up exciting possibilities, yet a complete theory of everything remains elusive. The intersection of time, space, and gravity is also profoundly affected by advances in technology. Instruments like the Hubble Space Telescope and more recently the James Webb Space Telescope have allowed us to peer deeper into space than ever before. We can now observe galaxies that formed billions of years ago, and by understanding the way light and time behave at these extreme distances, we are gaining insights into the evolution of the universe itself. In addition to observational tools, experiments at the cutting edge of physics, such as those conducted at the Large Hadron Collider (LHC), help us test these ideas at fundamental levels. The LHC, by smashing particles at nearly the speed of light, allows us to explore the fundamental forces and particles that make up our universe. This can lead to new discoveries about how gravity works at quantum scales or how time behaves at these extreme energies. Moreover, the study of black holes and the exploration of time near these enigmatic objects continue to provide new insights into the fabric of spacetime. The discovery of the first-ever photograph of a black hole by the Event Horizon Telescope in 2019 marked a groundbreaking moment in modern science. Such discoveries force us to confront the limits of our understanding, as they directly challenge how we think about the nature of time, space, and gravity. In everyday life, the effects of relativity are usually so tiny that they don't have a noticeable impact. However, on large scales, near black holes or when traveling at close to light speed, these effects become crucial. As we continue to probe the far reaches of space, studying phenomena like the expansion of the universe, the potential for time travel, or the behavior of gravity at extreme scales, we may one day uncover new laws of physics that could radically change our conception of the universe. One of the most fascinating concepts that continues to excite scientists is time travel. While it's often the stuff of science fiction, the real science behind time travel is rooted in the very theories we have discussed: special and general relativity. Under certain conditions, such as the presence of a massive rotating object or the bending of spacetime around a black hole, theoretical physicists have proposed scenarios where time loops or curves could exist, allowing for travel backward or forward in time. However, these are still hypothetical, and many paradoxes arise when trying to make sense of such possibilities. Newton's understanding of gravity was good enough to allow us to fly from the Earth to the Moon. Ever find yourself lost in the ticking hands of time, wondering if our understanding of it is just the tip of the temporal iceberg? On its head, his revelation is not just a theory. It's a key that could unlock the doors to the mysteries of the cosmos, revealing a universe more intricate and inspiring than we ever dared to imagine. How does Brian Cox's new theory challenge our traditional understanding of time? And what are the potential implications for our perception of reality? Join us on an intriguing exploration through the annals of time itself as we delve into Brian Cox's recently revealed groundbreaking theory on the nature of time in the vast universe around us. Mysteries are waiting to be uncovered, and some of these mysteries involve puzzling things about time and gravity, which are essential parts of our existence. Imagine a world where time acts strangely. It can either slow down or speed up. Also, the force that keeps us on the ground might not be what it seems. This is the realm of Albert Einstein's theories of relativity, where our understanding of time and gravity takes a peculiar turn. Albert Einstein, a well-known name, provided us with a new way of looking at the universe through his theories of relativity. His work laid the foundation for understanding how time behaves in different situations, especially when traveling at extremely high speeds. It all began in the early 20th century when Einstein proposed two groundbreaking theories: the special theory of relativity and the general theory of relativity. The special theory of relativity, published in 1905, transformed our understanding of time and space. In simple terms, it tells us that the laws of physics remain the same for all observers who aren't accelerating, regardless of their motion. This theory introduces the idea of relativistic effects, including the famous notion that time can dilate or slow down under certain conditions. One fascinating thought experiment used to explain time dilation is the light clock. Imagine being inside a spaceship moving incredibly fast, almost at the speed of light. Inside the spaceship, there's a beam of light bouncing between two mirrors perpendicular to the direction of motion. According to the laws of physics, the speed of light is constant for all observers, so the light beam must appear to travel a diagonal path. Now here's the interesting part. The time it takes for the light beam to travel its path should be the same for both the observer inside the spaceship and the one outside. But since the path is longer for the outside observer, it seems like it would take more time for the light to complete its journey. This apparent time difference between the two observers is what Einstein called time dilation. Time slows down for the observer in motion relative to the stationary observer. So, in this scenario, time behaves differently depending on your motion. Understanding how things change when they move fast, known as relativistic effects, is not just a theoretical idea. Scientists use big machines called particle accelerators like the Large Hadron Collider to make particles go super fast, almost as fast as light. When things move this fast, we have to think about time in a special way to make accurate predictions and measurements. Albert Einstein came up with the special theory of relativity in 1905, and it changed how we see the universe, especially when it comes to time and movement. This theory challenges what we might naturally think. It says that the rules of physics are the same for everyone, even if they're not moving. This is different from our everyday experience, where we might think that if something is already moving and we add more speed, it gets faster. But Einstein's theory says there's a maximum speed that nothing can go faster than, and that's the speed of light. In this way of thinking, events that seem to happen at the same time for us might not seem that way for people moving around almost as fast as light. Another thing that comes from this special way of looking at things is length contraction. This means that if something is moving, it looks shorter in the direction it's moving when you look at it from a spot that's not moving. And then there's this famous equation. Energy equals mass times the speed of light squared. That comes right out of this special way of thinking. It shows that energy and mass can change into each other, which is a big deal for understanding how tiny particles act when they're zooming around really fast, and also for things like what happens when atoms split in nuclear reactions. In the real world, special relativity isn't just a fancy theory. It's something we use in everyday technologies like GPS. When GPS satellites send signals to your device, they're moving, and because of this motion, time behaves a bit differently for them. If we didn't consider this time dilation effect in our GPS calculations, your navigation would be way off. So, special relativity teaches us that time isn't the same for everything and everywhere. It depends on how things are moving. This idea challenges what we usually think about time and space. It's like saying our normal understanding of the universe is a bit off. According to the special theory of relativity, time isn't fixed. It's influenced by motion. Some fundamental ideas, like the speed of light always staying the same and how energy and mass are connected, have been proven by lots of experiments. But there's more. Enter Albert Einstein's general theory of relativity from 1915. This theory goes deep into the relationship between gravity and how the universe is put together. It shakes up the old idea that gravity is just a force that pulls things from a distance. Instead, it tells us that gravity happens because space and time are curved or bent. It's like saying, hey, gravity isn't a mysterious force. It's just how things naturally move in the universe. According to Brian, understanding general relativity means thinking about the universe as a four-dimensional thing, combining 3 dimensions of space and 1 of time. In this framework, big things like stars, planets, and even us affect how space and time are shaped around them. This shaping is what we see as gravity. Imagine space-time like a big stretchy blanket. When something heavy, like Earth, is put on it, it creates a dent in the blanket. If you put something smaller, like a ball, near Earth, it will roll toward this dent. This is similar to how objects act because of gravity, not some mysterious force, but a reaction to the bending of space-time. It's like the Earth creates a little divot in the space-time blanket, and things move according to that dip. General relativity provides a solid explanation for how things move in our solar system, like the planets going around the sun. It can accurately tell us the paths these planets take, including how Earth follows an oval-shaped orbit around the sun. According to Brian, this is different from the old idea of gravity just pulling things together, which had a hard time explaining how planets move like they do. The new idea is that space and time are curved like a bendy fabric, and that fits better with what we see.